This is section 3.3. 3.3 is about scalar multiplication and unit vectors. Okay, you'll find some of this stuff to be pretty familiar. Specifically, we've done scalar multiplication before, we just haven't talked about what it really looks like. And then a unit vector is pretty predictable. Okay, the length or magnitude of a vector. Okay, before to find the length of a vector, we had to use the distance formula. Okay, now because our vector already has the subtractions done, if you remember that first component, u1, was really b1 minus a1 for the 2 points we were dealing with. And then the u2 vector was the b2 minus a2. Well, because that subtraction is already done, we just get u1 squared plus u2 squared, the square root of that. Okay, so it's still the distance formula. It's just that since the subtraction was already done, it's pretty quick to find the length. Now the notation for it looks like double absolute values. Okay, a lot of people even call it that. Sometimes it's also called the norm. You'll see that written a whole lot. So instead of length, they might say the norm of the vector. Okay, but just square the components, add them together, take the square root. For example, if u is AB, and this is where A is the point 34 and B is the point 5, -1, I want to find the length of u. All right, well, first of all, I probably ought to go ahead and find the algebraic vector AB. So I'd want to do 5 minus 3 and get 2, and then -1 minus 4 and get -5. So my algebraic vector is 2, -5. Now to find the length, remember all I do is take the square root of 2 squared plus -5 squared. 2 squared is 4, 5 squared is -5 squared is 25, and I just get the square root of 29. So this vector u is square root of 29 units long. So it's 5 point something units long. All right, scalar multiplication. To multiply a vector by a scalar, just multiply all the components by the scalar. Again, we've done this. We've done this with matrices, right? We did 2 times the vector 3, -1, and we got that that was the vector 6, -2. So you just essentially distribute the 2 to every component. So I get 2 times 3 and 2 times -1. Okay, now what that does as far as a picture is if I take the vector u, which was 3, -1, and I draw its position vector, I want to go from 0, 0 to the point 3, -1. Okay, that was u. That was the position vector for u. Now if I double that, I'm going to not go to 3, -1, but I'm going to go to 6, -2. That yellow vector now is the vector 2u. As you see, it's in the same direction, it's just twice as long. Okay, 2u was 6, -2. All right, so as far as the geometric vector, all that happens is that it's twice as long, same direction. All right, so scalar multiplication. If u is a vector and c is a scalar, and v is equal to c times u. So v is equal to a number times another vector. If c is greater than 0, if it's a positive number, then v is in the same direction as the u. We saw that with the previous example. In that example, our c was 2, and you saw it was in the same direction, it was just twice as long. If c were less than 0, v would be in the opposite direction from u. Okay, had I multiplied by -2, it would have started still at 0, 0, but it would have pointed the opposite direction, but twice as long. Okay, so the negative is just going to change directions. Then I saved this one for its own page because it seems to confuse a lot of people. What this is saying is that the length of v is equal to the absolute value of c times the length of u. Now you might be going, what the heck? Well, it goes back to the fact of, well, for example, the example we looked at. If you have the vector u and then I double it, it's going to be twice as long, right? Had I multiplied by -2, though, because length can't be negative, the new length would have still been twice as long. Okay, so it turns out to be the absolute value of c because of the whole fact that length can't be negative. Okay, so if v is c times u, then the length of v is the absolute value of c times u. Okay, for example, if I have a u, 2u is going to point in the same direction and be twice as long. What's negative 1/2 of u going to look like? Negative 1/2 of u is going to point in the opposite direction and be half as long. Okay, it's not negative 1/2 as long. The negative just denoted the direction. The 1/2, though, the absolute value of negative 1/2, gave me the difference in the length. Okay, now parallel vectors. All this business about multiplying a vector by a scalar is going to give us the concept of parallel vectors. The vectors u and v are parallel provided there is a non-zero scalar c such that v is equal to cu. In other words, one is a multiple of the other. If that's true, they're parallel. Given that u and v are parallel, find a if v is the vector a4 and u is the vector 3, -2. Okay, the key to understanding this problem is to catch the fact that it says they are parallel. Because they're parallel, we know that v is equal to c, some value, some number, c, times u. All right, if I can figure out the c, I can figure out the a. So start by setting v to equal to c times u. All right, there's v, a4, equals c times u, 3, -2. All right, now you remember to multiply by a scalar. I want to distribute the c to both of the quantities, so I get 3c and -2c. All right, from that bottom row, I get that 4 is equal to -2c. What's that mean? 4 equal to -2c means c is equal to -2. All right, great, I've got the value for c. All I need to do now is just plug it in, and I've got a equal to 3 times c, right? So a equal to 3 times -2, so a is -6. All right, so not too bad, right? Next, subtraction of vectors. We talked about addition of vectors. Specifically, we said to add u and v, we would need to draw a parallelogram and have u plus v be the long diagonal of that parallelogram. Okay, or the diagonal, if you want to think of it, that starts at the intersection of u and v. All right, what if I wanted to do subtraction? Well, turns out it's just that other diagonal. Now, because it's u minus v, I want to start at v and actually go to the end of u. So start at the end of v and go to the end of u. That's going to be the vector u minus v. Why, you might ask? Well, I thought you might ask that. It's because if you have your vector u and you want to do u minus v, that's the same thing as u plus -v. Now, as you can see, I slid u over to the right. That's because I want to draw the vector -v. -v goes in the opposite direction, but it's the same length as the original v. The original v went over to the right, so -v is going to go over to the left. Now, if I do that like it's a sum, the diagonal there actually turns out to be the shorter diagonal, but it's the diagonal that starts where u and -v intersected. Okay, that was the important part of that. I think I misspoke it earlier. But it starts where u and -v intersect. That is going to be that sum vector. So that's going to be u plus -v, which in this case is u minus v. Okay, and as you see, that's the same u minus v that I got from before. It's just over to the left of where I drew it before. And remember, with vectors, the location isn't important. It's the length and the direction we're going for. All right, next, definition. This is the one I said you could predict. A vector u is a unit vector, provided its length is 1. In other words, there's that symbol again, the double absolute value looking things. Remember that means length or norm. That is equal to 1. Okay, so looking at an example, if u is the vector 1/2 root 3 over 2, that's going to be a unit vector. I can always check by just doing the formula there. It's equal to 1/2 squared plus root 3 over 2 squared, the square root of that. So I would get the square root of 1/4 plus 3/4, which is the square root of 1, which is 1. So that really and truly is a unit vector. Okay, let v be a non-zero vector. Then u, which is equal to 1 over the length of v times v, is a unit vector. Let's try to figure out what the heck they're saying here. Okay, they're saying if we take any old vector, some non-zero vector, we can get a unit vector in the same direction as v by just dividing v by its own length. All right, so for example, if something were 2 units long, if v were 2 units long, and I divide v by 2, bam, it's 1 unit long. Or if it's 8 units long and I divide it by 8, now it's 1 unit long. Okay, so not too bad once we kind of figure out what they're talking about. For example, let's say v is the vector 3, 4. Find a unit vector u in the same direction as v. Okay, I want to follow what it said to do, which was u is going to be equal to 1 over the length of v, so that would be 1 over root 3 squared plus 4 squared times v. So I just get it's a fifth of v. V was 5 units long. If I multiply v by 1/5, I now get something that is 1 unit long. So 3/5, 4/5 is going to be 1 unit long. And you can check and make sure that it is. You do get 9/25 plus 16/25, so you get 25/25, which is 1. Suppose we didn't want that vector to just be 1 unit long. Suppose we want a vector w parallel to v such that the length of w is m units long. I want to be able to specify how long it is. I don't want it to just be 1. All right, so I want m to be some value greater than 0. W is going to equal, the easiest way to find it is m over the length of v times v. Now you remember what we did before. To make it 1 unit long is we divided by the length of v. Now to make it m units long, we want to multiply by m. So it's pretty simple, right? I want to divide by the length to make it 1 unit, and then multiply by m to make it m units. That's going to be m units long and in the same direction as v. What if I wanted opposite direction? I just multiply by negative, right? Okay, and that's what we're going to do in this example. Find a vector w which is 3 units long and in the opposite direction from 3, 4. All right, so in this problem the m is 3. All right, well w is going to equal, notice I have a negative to start with. That's because I wanted it to be in the opposite direction. That's all that negative is going to do, is just put it in the opposite direction. Then on the top I want to multiply by the 3 because that was my m value. Divide by the length of v, so I have divided by the square root of 3 squared plus 4 squared, then multiply that by v. So if I were to figure out negative 3/5 of v, that would give me a vector 3 units long and in the opposite direction from v. So w would equal negative 9/5, negative 12/5. And you can double check that that really is 3 units long. And the negative is going to guarantee it's in the opposite direction. So they are parallel, it's just w is in the opposite direction from v. Okay, next we need some basic unit vectors. They're called basic unit vectors because it's pretty much the simplest vectors that you can find, as well as the fact that you can write any other vector in terms of these vectors. Okay, so 1, 0 is I, and 0, 1 is j. Now this is a different I from the square root of -1, the imaginary I. It's completely different. This is a vector I. Okay, let's see what I meant about writing one in terms of the other. Write 3, 4 in terms of the basic unit vectors. Okay, well 3, 4 is equal to 3 times 1, 0 plus 4 times 0, 1. In other words, 3, 4 is 3i plus 4j. Okay, so whatever's in front of I is the x component, whatever's in front of j is the y component. So now I hope you can see why we call it a basic unit vector. It's pretty simple to convert anything to terms of I and j. Okay, so how did that section seem? Was that pretty good? All right, as you saw in the end, we talked about I and j. Now what they're going to do now is go back and give you all of your previous problems in terms of I and j. It's not bad, though. You'll see some problems in the next section. You'll probably also have some problems in the homework where they start talking about I and j a lot. So get used to that notation. Not too bad.